Okay. Hi, everyone. I'll be presenting our paper, Exposing Privacy Risks in Anonymizing Clinical Data Combinatorial Refinement Attack on K-anonymity Without Auxiliary Information. Yeah, I know it's a mouthful, but yeah, so this project was a collaboration between George Mason University and Mason and Partners Clinic. Mason and Partners Clinic is a really small, low resource clinic that works with marginalized people in the society. And this got us thinking about what is the privacy when we deal with people who are not well represented in multiple data sets, or they wouldn't exist in voter ID, or they wouldn't have information in other data sets except for this maybe clinical data set that is recorded at Map Clinic. And before I get into the details of my paper, I would want to draw our attention to the fact that we need to think about how often clinical data is shared. Um, When we look at the statistics, more than 300 million patient records are exchanged across healthcare systems. 70% of the hospitals engage in clinical data exchange across providers, and approximately 77 individuals worldwide are willing to share health data for health improvement. These all are really substantial numbers, so it makes us wonder if the privacy of this data is not up to the standards, then what could be the consequences of that? So when we think about sharing this medical data, there are generally two ways of doing it. One is aggregate statistics, which is shown on the left. And an example of that would be to give the number of male and female patients in a hospital. And the other one is microdata release, which would be much more richer information. It's in the form of data records where we can have attributes such as age, gender, and a health condition. Um, the second one, that's microdata, is much more useful for analysis. And that's why in this paper, we focused just on microdata. So a, a very popular regulatory compliant de-identification method is k-anonymity for de-anonymizing microdata. We can think of k-anonymity as kind of blurring a picture. In the first picture, we have maximum utility. What does that mean? I know who the person is in the picture. I know what they're doing. I know where they are. I know what the time is. I know all these details, but there's no privacy. If I increase the blur, I don't know the identity of this person anymore, but I still have some utility. That means I can tell they're working on a desk. I can maybe tell their gender, and I can also maybe kind of guess the expression. So that's what k-anonymity does. It kind of blurs the data. So if we have the original raw microdata where the exact values are given, I will blur it by increasing the generalization or the intervals, the granularity of the data. K-anonymity is very popular. It is HIPAA and GDPR compliant, and it was introduced in 1990s. But despite its popularity, k-anonymity has been repeatedly shown to be not secure by various attacks. These attacks are, I have categorized them into three categories, and all of them kind of share a common theme. For example, the first category is that they require some kind of auxiliary data. The second one is they require some kind of background knowledge. And the final one is they require some kind of distributional knowledge. When we think about this, there's kind of an easy assumption to make. Can we say that k-anonymity is secure in the absence of any auxiliary data? This kind of ties back to my introduction about Map Clinic. Because they only work with people who are not well represented in other data sets, does it mean that if we just k-anonymize their data set and release it, Is it secure to do that? Is it fine to do that? And so our attack proves that it's not. It says that even without auxiliary information, anonymized microdata can still leak private information. Yep. And so before I actually go into what k-anonymity is, what our attack does, how are we using information to like get private information about patients, I want to give a little idea about like a little background knowledge. There are two flavors of k-anonymity. One is global recoding and local recoding. Global recoding, in global recoding, every attribute is generalized in the exact same way. What does that mean? If you look at the age attribute, every record is generalized to the interval 50. And if you look at the weight attribute, every record is generalized to the interval 50 as well. This is coincidental. It could have been generalized to a different interval, but in the same attribute, it is generalized identically. But if you look at local recoding, there's a little more flexibility here. The first three rows are generalized to the interval 25, and the last three rows of age are generalized to interval 50. For analysis, this gives us richer information. And so for our attack, we will focus just on local recoding because we care about the utility of the data. Now, k-anonymity has been around for ages. There are so many tools that implement it. These are just a few that do it. And out of these, ARC's anonymization tool is a really popular one. And again, I'm just giving background. So we focus on ARC's anonymization tool, and more specifically in k-anonymity, we focus on local recoding. Why ARCs? It is popular, but why did we decide to focus on ARCs? This again ties back to the kind of data we're dealing with. We're dealing with a data from a clinic that has low resources, so it's important that the tool be open source. It is important that it should be actively maintained, and it is important that it has some policy recognition. ARCs does all this, and also it has been used in multiple healthcare and clinical research before. So we decided that ARCs is the tool that we need to like dive deeper into, understand what exactly is happening in the local recoding algorithm. Okay, so before we understand about the attack, again, a little more background information. Most of the k-anonymity operates on this data structure called generalization hierarchy, because we want to generalize each record to an interval. How are these intervals picked? We have a tree that has that the lowest level has the finest grain intervals, and as we move up the hierarchy, they progressively get merged to broader intervals. For example, every attribute here has a separate generalization hierarchy. So the attribute Q1 has a generalization hierarchy on top, and Q2 has generalization hierarchy too at the bottom. Just to keep things simple, I've made it identical. But yeah, they could be different. All right. So if we just take the first three records in Q1 and we want to generalize it, we can do that by using a node in layer 1 of generalization hierarchy Q1. And we can do the same by using a node in layer 2 of generalization hierarchy. Sorry, yeah, you have a question.
Q1 wasn't the first one 23?
Yeah, okay. It's supposed to be 28, sorry. Yeah, you're right. So it has to be in the interval. Thanks for pointing that out, yeah. And the second one is from 1 to 50. What happens after we've generalized these three records is that they look identical to each other. And there's no way of distinguishing and them, like telling them apart from each other. And so this group of indistinguishable records is called an equivalence class. And We can do the same for the bottom 3 records, and they form an equivalence class too. Now that this data set has 2 equivalence classes of size 3, so we can say it's k-anonymized, where k is 3. In general, a k-anonymized data set is said to be k-anonymized, sorry, if it has at least k indistinguishable records in each equivalence class. So the size of equivalence classes can be greater than k, but they should not be less than k. All right, so we've understood what generalization hierarchy is, what k-anonymization is. This is a new data structure that the ARCS algorithm introduces itself. So we know what a generalization hierarchy is, and we want to use the ARCS algorithm doesn't generalize one attribute at a time. It will generalize all attributes of the data set together. So we need to look at the combination of the generalization hierarchies, and that's exactly what the generalization lattice does. If you see, each node is a combination of the layer of each hierarchy. So for example, the bottom has 0, 0, which means it's raw data. I haven't generalized it at all. But if we move a little up, which is this node that's highlighted, which is layer 3, layer 1, it means that attribute 1 has been generalized to layer 3, and attribute 2 has been generalized to layer 1. I'm going to stop for questions if you have any. Okay. Yeah, so we know that the bottom has raw data, and as we progress up, the level of generalization increases. And as we move to the top, this is the maximum generalization, and it corresponds to the root node of all the hierarchies. This is when we have maximum privacy, and the data has been generalized to the entire range of values. So for example, it's 0 to 100. We cannot tell what the granularity of the data is. We can't tell anything about it. This is as good as having an opaque image. This is the worst case scenario for utility. Okay, so this is the most important part about the presentation, is the greedy nature of ARCs. This is exactly what we exploit for getting more information about the data and breaking the locally coding algorithm. The point of having the generalization lattice is to help ARCs traverse the different generalizations. It gives us like a traversal space, and it goes through the lattice node by node, checking if that generalization makes the data k-anonymous or not. If it does, then it marks that node as k-anonymous, or in this example, it marks that node as green. Once it's done traversing, it will pick the node with the least generalization or maximum utility. So this means that the ARCS algorithm is picking these nodes in a greedy way. It wants to pick a node with maximum utility. It wants to pick a node with least generalization. Right. So I would just like, before I move on to the next part of it, which is segment grid, I just want you to think about, because it's forming these anonymous equivalence classes according to this greedy algorithm, there is a structured way about, in a way in which it goes about this anonymization. These equivalence classes, yes.
Like the greedy algorithm is given some bucket sizes. How does ARCS choose the bucket size?
What do you mean by the bucket size?
One, like
Mhm.
there are two, the
Oh, the interval sizes, yeah, yeah. How does it choose the interval size? Um, right, that's okay. It will pick, I'll explain this from the beginnings, and maybe if it makes sense, then it answers your question, let me know. So what ARCS does is that every node has the generalization that it can apply to the data, right? So it will take the generalization, apply it to the data, check if I formed equivalence classes that are at least k in size after I've put them in those buckets. And if it's not, then I proceed. And I keep doing that and I keep marking nodes. So I'm not picking a fixed bucket size. I'm just going around checking which ones are anonymous. And then out of everything that's anonymous, now I want to decide, okay, now all these work for me, all of these give me privacy, but I want to pick something that also gives me a utility. Because in the end, I want to share this data to for analytics so that I can actually get some information out of it. Best case scenario, I can just go for the top node, have maximum privacy, have the biggest bucket. But I want a bucket that's small enough and also gives me privacy. So that's how it picks what bucket size wants to. Yeah.
First, I assume this is for many attributes, you're just showing the two attributes.
Yes.
The other question is, if the bottom node was not green, is there a preference between the two nodes at the same level, or then?
Yeah, there is a preference. So this is like a really specific way it works in. It will check with the between those two. Suppose here it's very symmetric. Both attributes go up to layer 3, right? One at for in like a really different situation, one attribute might go up to like layer 4, another might go up to layer 2. So it will compare like at what ratio out of all the levels have I gone. Like suppose if in one I've only gone up 2 out of 4 levels, and the other I've gone 1 out of 2 levels, compared to a node on the same level of the lattice where I've gone 3 out of 4 instead of 2 out of 4 or 1 out of 4. It'll do that kind of comparative analysis between how much I've progressed in each.
So there is some sort of metric.
Yes. Okay. Okay. So now because these equivalence classes are not formed arbitrarily, they reflect some structural decision made during the traversal of the generalization lattice. And to like systematically analyze these structural patterns, we need a way to represent the data space. And this leads us to the segment grid. This is something we introduced in our paper, and it helps us visualize how the data space is partitioned. So each cell in the grid is called a basic segment, and we can see that it's labeled B1 to B16. You can think of each basic segment as like the finest grained generalization possible, and it corresponds to the lowest level of the generalization hierarchy. So for example, P1 here has 1 to 25 in generalization hierarchy 1 and 1 to 25 in generalization hierarchy 2. And we can see that. Since these correspond to like generalizations, we can also merge them to form bigger buckets or like bigger intervals. For example, the purple box that we see has been merged along attribute 2. So now it represents the bucket 1 to 50 along attribute 2. And because we can like play around with these basic segments to represent different bucket sizes or different generalizations, we can actually use them to represent equivalence classes. As like indicated, like is shown on the slide, the um, purple group corresponds to the first equivalence class, and the blue one corresponds to the second equivalence class. Yep. Okay, now we have a way to represent the data space. And we know about the greedy nature of arcs. We can finally get down to like using the information we have to like actually get break the privacy. Okay. Um Cool. So, as I talked earlier, there is a very systematic way in which ARCS goes about selecting equivalence classes and using the traces it leaves. But while making these equivalence classes, we can derive certain inferences. Um, the first such inference is called the halves inference, and which is that for every half of an equivalence class, I'm going to start calling these segments equivalence classes, these groups of segments. So for every half of equivalence class, there must be at least one record in them. Now, why does that happen? As I mentioned earlier, the ARCS algorithm is greedy. It wants to form the smallest possible equivalence class in the segment grid. So it will form if it could have formed something smaller, it would have selected that, which means if the halves, one of the halves was empty, which means there's no record there to generalize. That means I wouldn't have even included that in my equivalence class, and I would have formed a smaller equivalence class. And this inference is directly from how the ARCS traverses the lattice, chooses the minimum generalization. So in this example particularly, if we see half one and half two, we can say for sure that both of them have at least one record in them. And similarly, if we see half three and half four, we can say that they have at least one record in them. So in the end, we have four halves for every equivalence class, and each half should have at least one record. Cool. Next we have the overlap inference. There can be situations where like the generalized regions can overlap with one another. And because the ARCS processes equivalence, and we know from like how the ARCS operates, it processes equivalence class sequentially. So it means that one of the equivalence class was formed before another. And in that case, it would have used up all of the points in the overlap region before the second class. In short, we can say that the area of overlap in the segment grid is empty for the second equivalence class. Does that make sense? I can pause for questions. Yeah.
Is it easy to distinguish which is the first and which is the second equivalence class?
Right. Yeah. Yeah. It starts by forming the smaller equivalence classes first. That's a great question. So because I want like the ARCS algorithm wants to form like lowest generalizations first, it will start by forming all the smaller ones. And so just by comparing the sizes of the equivalence classes, we can tell which was formed first. Yeah.
So if those triple squares were empty, what would the shaded regions actually look like?
If the purple regions weren't empty, can you explain what that means? Like,
given these structures of shaded regions, you can put purple regions in.
only for the second equivalence class. Because the first one has kind of stolen those records. It's used it up. So now the second one just has to use the second. It doesn't have any of those. Okay. Okay, this one, the last inference is pretty straightforward, but it gives us a little more information about how records are distributed. Anything that's, yeah, sorry.
So for the second one, like why is there even an overlap if ARCS is greedy and tries to minimize?
Yeah, because of how the generalization hierarchy is defined. Because there's an interval from 1 to 100 and there's no interval 1 to 75, it will have to take the whole bucket. But if the generalization hierarchy had an interval 1 to 75, it wouldn't have formed that. Great question. Yeah, finally, we know that anything that's not anonymous, by definition, it means that it's going to have fewer than k records. And so any basic segment that is not an equivalence class is going to have less than k records. Okay. So far, we've seen the greedy nature of the arcs, we've seen the inferences, we've seen overlaps, non-anonymous, but what does this even mean? How is this even useful? So what it does is that we systematically combine all these inferences to carry out the CRA. And we do that by translating these inferences into constraints and then using linear programming to solve for all the feasible values of like how records are distributed across the segment grid. And finally, we can find smaller or like less obvious ways of like reducing the all plausible values that exist. Okay, so more specifically, like we introduced a new variable called Z. And for each basic segment B, we have a value Z, which represents the number of records in the basic segment B. So for example, B1 corresponds to Z1 and B16 corresponds to Z16. We can now start seeing how these inferences translate into constraints. For example, if you remember the halves constraint, we know that each half must contribute to at least one record, but fewer than k records, because if it had k records, it would be an equivalence class itself. And so we can say that, sorry, it's been messed up because I moved to like PowerPoint, but I'm going to just read it out. So yeah, we can say that the sum of all zi's, for example, for half one, we can say the sum of all zi's for like bi belonging to half one have to be greater than 1 and less than k minus 1. And we can do the same for all the halves. Similarly, since the overlap's empty, we can say for the equivalence class 2, the zi's are equal to 0. And for non-anonymous basic segments, the sum of all the zi's should be less than k minus 1. Yeah. So before we had these constraints and we use them to eliminate the infeasible integer values. So anyway, I'm going to start that. We can think about using the linear programming of the constraints as a funnel. We start with a large possible distribution of like number of records in the segment grid, and then using linear programming, we narrow it down to much smaller possible assignments. And for this linear programming, we have no objective function. The only goal is to find all the feasible assignments to Z. Yeah, so what does it mean to have, what are the plausible values that exist? For example, in the equivalence class, which is in purple, we have values that range from, we have all integer values. The number of integer values are 25 times 50. And if the k value is 3, then the possible values that exist, possible integer values that can exist in that equivalence class are 25 times 50, choose 3. And similarly, for the second equivalence class, this value is 50 times 50, choose 3. And using linear programming, we can significantly reduce the number of these plausible values.
Quick question.
Yeah.
Do we know that all three have to be distinct or something?
All, oh yeah, that's an assumption that we make, that all have to be distinct. And like we made that assumption because if we have like a medical record, it's very hard for them to be overlapping for all the parameters and all the records that we take. So that was an assumption made on our part. Okay, so to quantify the reduction that we introduced a metric called the CRA ratio. which is the ratio of all the plausible solutions without CRA to the plausible solutions with CRA. And finally, for our experiments, we evaluated our attack using two real-world data sets. The first one was from the map clinics, and it contained like de-identified patient attributes such as weight, age, and blood pressure. And the second is a clinical subset of the EdgeCup dataset, which is commonly used in healthcare privacy research. We anonymized each dataset using arcs, underweighting k values from 3 up to 10, up to 8, and analyze the results using the CRA framework. And for each configuration, we measured the total number of plausible assignments before and after applying CRA to compute the CRA ratio. And so this is like one of the results we got. And something that's interesting is that CRA becomes more effective as K increases. As you can see in this, where CRA ratio reaches 10 to 4 for EdgeCup with 4 attributes. This is very counterintuitive because higher value of K is supposed to mean more privacy. Yeah, sorry.
Can you go back to the definition of serial ratios?
Yes.
Okay, yeah, sorry. Done. Possible values means values of like what the actual attribute value is.
The plausible values mean what the value of the record would be.
So like what the age is, or
What the combination would be.
I'm sure I understand. So would it be for like record number one?
Mm-hmm. It would be like age 50 and some like heart blood oxygen level 82. So
This one plausible value.
this one plausible value of a record. Is that
Yeah.
okay? So yeah, so for our results, we saw that as the value of K increases, the CRA ratio increases as well. And this is very counterintuitive because larger K means bigger buckets, bigger groups, and the probability of identifying someone out of them is 1 out of K, 1 over K, and that should mean more privacy. But our attack becomes more effective with higher values of K. And this is for the map clinic data set. We saw a similar result there, but the CRA ratio was as much as 10 to 3. Let's say thank you. So to conclude, we've introduced a new family of combinatorial refinement attacks for locally recorded data, k-anonymized data, and it requires no auxiliary information. It is purely based on the way the algorithm operates, and it has exposed a gap between what is the perceived and the actual privacy of locally recorded k-anonymized data. Thank you.
Questions? I have a question about the CRA ratio.
Uh-huh. Should have shared. About. Yeah, you can ask.
Mentioned the larger K
So,
increases like the top 5. Yeah. Yeah, slide that actually for this one, we mentioned that the larger K interestingly enough increases the CRA ratio. So that means the attack is more efficient.
yes, it's more efficient.
Because larger K also means larger forget if it's the denominator was it without or with CRA.
Yeah, sorry. Denominator is total values width.
Yeah, I'm wondering whether, whether this ratio, like whether the numerator and the denominator, how they grow as k, because I understand the ratio is, but the numerator also grows very much, right? It's like as you increase k, like with this, yeah, binomial number, right? Goes, it explodes, right? So I'm wondering whether the, yeah, if you have an insight, like what's going on with the numerator, plus increase k.
Yeah, okay, so for the numerator, like you said, the interval value should remain the same, right? 25 times 50, that's not changing. The only thing that's changing is to choose 3 or to choose k value, right? Um, if I'm not wrong, like if we have a larger value for like choose k, doesn't that reduce the value? It's like 5 choose, no, sorry. Um,
And then understand something on basic. What is the ratio supposed to? Is it supposed to show how much you're able to be anonymous?
it's supposed to show how much so initially when we start, there are like certain ways we can distribute records in this segment grid. And initially we can distribute them arbitrarily anyway in the anonymized in the equivalence class, but after using these constraints, there are only certain regions that they can take up depending on the constraint. And so that limits where how you can distribute it and where they can exist. And so it limits what values are possible for every record.
Right, so go back to where should we look at one phrase for showing what would be the ideal number of all possible ways that,
Yeah,
that and then the number is what is the actual feasible line.
right. Yeah.
It's one that larger ratios. I'm sorry, I'm confused.
If the numerator is larger, that means if the numerator is much larger than the denominator, then you will get a higher value for the ratio. That means compared to what we started with, we have reduced it quite a lot, so the ratio is going to be high. And that's why a high ratio means a more effective attack. Yeah.
Evgeny's raised his hand.
Oh, yeah, I think.
Yeah, sorry. Yeah, sorry to interject. Let me try to answer the last question if I heard it properly. So a couple of things are happening at the same time. The first is that because you're raising the K, this means that you have a higher standard for privacy. You require more records to participate in order to form a group, the equivalence class, right? So this increases the privacy, which means that the previous standards, let's say for K equal 2, are not enough. You have to incorporate more records for K8, for example. And because of that, the ARCS algorithm tends to get like wider equivalence classes in order to incorporate more and more data because K is so high. And because of that, and that's the interesting insight of our technique, because of that, you have more overlaps. You have more constraints that are active. So in a sense, you are correct that indeed the ranges are wider because it's necessary in order to form this high K value. But also at the same time, our attack is more effective because you have more and more constraints, so you can eliminate more noise from the plausible assignments. Does this answer the question?
Yeah.
One question.
Maybe I'll ask a question about the graph in the next slide. Do you have any intuition for why it's sort of somewhat funnily looking shape? It's like it's not like a nice line, so to speak, or like an exponential. Like, why does it plateau in the middle? Is there anything special behind this?
Um, I think we just, and I mean, I guess if anyone can tell if he has a different opinion, but I think it's very data dependent on how these equivalence classes are formed. We just wanted to see a general trend on how the CRA is performing with different values of K, but in the end, how these equivalence classes are formed and what sizes and shapes they're formed also depends on the kind of data we're given. Um, and so it's not going to have a very clean shape because there is a factor that plays because of how, yeah, the data is. Yeah.
But clinic you worked with,
Mm-hmm.
what did they do in response? Like, did they try changing anything to increase privacy?
I think for them, if this was just a way to see like was k-anonymity a viable option to like anonymize their data set, but we did reach out to ARCS and they did add a disclosure on their website that the local recoding algorithm has this flaw and whoever uses it should yeah know about it. Keep that in mind.
Do you know if there's some sort of result, like, if you use the ARC's k-anonymity algorithm, you can still for sure get, let's say, k/2 like you can still guarantee that you have some level of anonymousness, even if you don't have what they claim.
If you can have some level of k-anonymousness, k-anonymity.
Yeah, like, so maybe you run the k-anonymity algorithm
Mm-hmm.
and there's a tax, so it's not actually k-anonymous, but maybe it's like j-anonymous for some smaller j. Is there some sort of,
No, we didn't explore that, sorry. Yeah.
yeah.
And what are common, like, are these K values very commonly used?
Yeah, so the K values that we used were after like checking what are the most commonly used and like 3 to like 7 or 8 is what they usually use.
And same goes for the size of the QI.
Mm-hmm. So we use the QI according to like the data set that we got from Math Clinic, but generally clinical data is like high dimensional, so that can be like more than this. Yeah. Yeah, any other questions? Okay. I think that's it then.
Thanks, speaker.